Okay, so here's another group theory problem. This one is saying let G be an abelian group and let K be the set of elements in G such that a to the second power is equal to 1, and we're going to define H as the set x squared where all of these elements are coming, where all the x's are coming from G, and we want to show that G mod K is isomorphic to H. So let's go ahead and begin with our assumption. So suppose that G is an abelian group. Okay, and we are going to define the sets above. So let me go ahead and copy those here. Oops, we want this. Copy, and we'll paste it here. So we define the sets just as we defined them above. So K again is that set there. And before we get started on anything else, we are going to reference the first isomorphism theorem. I'm using Dummett and Foote's abstract algebra book, but I think some other textbooks call this the fundamental theorem of homomorphisms, I think. I'm going to call it the first isomorphism theorem. That's what I know it by. So let me go ahead and state this here. The first, let me use a different color. The first isomorphism theorem. Which says that if you have a map phi from G to H, which is a homomorphism of groups, then two things happen. Then the kernel of phi is a normal subgroup of G, and G mod its kernel is isomorphic to the image of G under phi. And this really sets the foundation for this problem here, because you can kind of see here we already have a very similar statement to what we want to show. So what we want to do here is define a map from G to H and show that not only is it a homomorphism, but it's also surjective, because we only get to conclude that G mod its kernel is isomorphic to the image. But if we can show that the map we will define is surjective, then the image will actually be equal to the domain here, or the codomain, which would be H, making it an epimorphism, I guess would be a more formal way of what to call it. So that's what we're going to do. So for the proof, we are going to define, and I'll go ahead and use phi as well. So define phi to be a map from G to H. And this map is going to take elements in G and send them to G squared, because H, this would be a map to H because G squared would automatically have to be in H, because that's the way we constructed H to be. So this is a map from G to H, which will of course be non-empty, because at least the identity will be in there, among other things. So we will show that phi is an epimorphism. Again, this is just a homomorphism that is surjective. Okay, so let's take two elements in G. So let's take, let's do, I guess, X and Y. Take X and Y in G. And again, as we've done before, to show that this is a homomorphism, we want to show that phi, I don't think this color is going to look very well, but whatever, phi of X, phi of Y is equal to phi of X, Y. This is what we want to show. to show that phi is a homomorphism. So phi of x, phi of y, and you can do this in any order, of course. This is just the way I like doing it. Phi of y. By the way, we've defined our map. This is just equal to x squared, y squared, which is equal to x, y, y. Now we want to recall that this map, what am I doing? That this map, or not map, but that G is abelian. Where do we have right here? G is abelian. So let's take advantage of that. This is going to be equal to x, y, which is just xy squared, which is really just phi of xy. So then we get to say that phi is a homomorphism. Thus, phi is a homomorphism. Okay, we want to show that it's also surjective. Again, to show that something is surjective, you want to show that no matter what element you take in H, you can find an element in G, such that when you apply phi to that element in G, it gets sent to that element in H. So you can always find something in G. So how do we do that? So we want to show, here, let me write it out. So suppose that, I don't know, we'll call some element H, which is going to be it's going to be of the form x squared. All right, because elements in H look like that, just some element from G being squared. We want to show that that there exists some element G in G such that phi of G is equal to H. Okay, so this kind of feels like a weird thing to prove because, I mean, we've defined our map to be able to do this. So it just kind of feels like you're just pointing out the obvious, like, duh, yeah, of course. So indeed, we have an element x in G, and when we apply phi to x, what do we get? Well, we get x squared, but that's just H in H. So yeah, it's surjective. Thus, phi is an epimorphism. I always think some of these surjective claims just feel like kind of, I don't know, obvious, but it's so obvious that you feel like you're doing something wrong. Okay, so we've shown that it's an epimorphism. So we have that it's a surjective map. What else do we need? We need to show that that K here is actually the kernel, because then we can say that G mod K would be isomorphic to the image, but then the image would just be H. So actually I should write that. Hence, because we're going to use this. So hence, the image of G under phi is just equal to the codomain itself. It's a surjective function. So phi of G is equal to H. So matching things up here, we have this. So there we go. We can place the H there for the map phi of G. We want G mod K to be isomorphic to, in this case, H, which we have that phi of G is equal to H. We want to show that K is actually the kernel of phi, which, again, just from the way we've defined it, it kind of just happens that way. Because, so let's say note that K is defined to be the set A and G, all of the elements from G such that A squared is equal to 1, which of course this is the identity element in G. And our map says that we take elements in G, we square them. The kernel of phi are all of the elements from G that get sent to the identity elements. But if we're taking elements from G, we're squaring them. K consists of all of the elements from G that when you do square them, you get the identity element. That tells us pretty clearly that K must be the kernel of phi. And thus, by the first TFI, the first isomorphism theorem, then G mod K is isomorphic to the image of G under phi, but that's just equal to H, which is what we wanted to show from the beginning. And usually I like to draw this little diagram that helps me remember this theorem. So if you have a map G, or not a map G, but a group G, and then a map, say, phi, that goes to the image of G, then the kernel of G, or the kernel of phi, is a normal subgroup, and when you quotient out by the kernel, then you have a unique map a unique map from G mod its kernel to the image of G, such that G mod its kernel is isomorphic to the image, which is always a subgroup of H. But then if you show that this map phi is surjective, then it's no longer a subgroup, but it's actually equal to this. And from this, we get to claim, of course, that G mod its kernel is isomorphic to the image of G, which in this case is equal to the entire codomain, which is what we've shown here. So that completes the proof here.